Welcome to our chapter, Technological Integration Probability. In this video we analyze the probability of technological integration regarding a future energy system based on low carbon emission and minimal cost for the region Europe, Middle East and North Africa, the EUMENA region in the year 2050. This probability is shown for the technologies dispatchable solar power and its transfer from the Middle East and North Africa to Europe, nuclear power and carbon capture and storage. The results show in a multi-criteria analysis the impact of each technology for the energy system. A transfer of dispatchable solar power from the Middle East and North Africa to Europe can reach a high probability of technological integration depending on the model region. In our scenario analysis, we evaluate the apparently competitive low-carbon emission and dispatchable technologies. These are concentrating solar power CSP, a transfer of dispatchable solar power, including high-voltage direct current, in short CSP HVDC, nuclear power and carbon capture and storage CCS. Hereby, each of the 15 model regions in EUMENA is analyzed separately in a framework of isolated regions. The technological integration probability of CSP HVDC, nuclear power and carbon capture and storage is determined by cost sensitivity scenarios. The use of an optimization model considering minimal cost as target function can lead to an exclusion of technologies due to minimal cost differences of technologies. To avoid this effect in the following, different cost relations of technologies are required. We show the possible combination of cost assumptions of technologies. These cost relation combinations arise 9 different scenarios. In addition to the described sensitivity framework, 2 transmission line technologies, overhead lines and underground cable, are analyzed. Consequently, the complete sensitivity includes 18 scenarios. Base cost assumptions. Maximum all, mean all, minimal all are set constant for all technologies. Only the examined technology is calculated with each maximum tech, mean tech, and minimal tech cost combination to the base cost assumptions of all other technologies. Thus, the probability of each cost assumption is assumed to be equal. Our cost assumptions can be seen in the reference and relate to a time value of money in the year 2015.
The results reveal the integrated capacity of the analyzed technologies as dots and capacity bandwidth. The box plots show the data using quartiles. The technologies are in Chart A, CSP HVDC, in Chart B, CSP, in Chart C, nuclear power, in Chart D, combined cycle gas turbine CCS, and in Chart E, coal CCS in each model region. The spread of the bandwidth depends on the input cost assumptions and the regional resource and demand profile. The results show the technological integration probability of CSP HVDC with up to 66%, CSP up to 89%, nuclear power up to 44%, combined cycle gas turbine CCS up to 56% and coal CCS up to 11%. It must be pointed out the missing of unit commitment constraints in the model. Thus, nuclear power and coal CCS are overestimated in their technological integration probability due to higher assumed flexibility and would therefore cause more storage demand in the system. Also, reducing carbon emission limits close to zero would exclude the CCS technologies due to their still remaining carbon emissions during operation.
The dispatchable technologies CSP, nuclear plants, combined cycle gas turbine CCS and coal CCS are analyzed in their system impact applying evaluation criteria such as system cost, infrastructure such as storage and power plant capacity, as well as grid and transmission line expansion, power kilometer, and operational behavior considering curtailment. In the spider chart A, the comparison of CSP, including CSP HVDC, and nuclear power plants in a zero-carbon emission scenario is illustrated. The other charts of B to D evidence the comparison of dispatchable solar power with nuclear plants, combined cycle gas turbine CCS and coal CCS in a framework with small CO2 emissions. The results of the zero CO2 emission scenario in Chart A and the low CO2 emission scenario in Chart B points out that the use of nuclear power plants lead to lower power plant and electrical storage capacity, curtailment, expansion of regional grid and point-to-point line expansion. Storage and curtailment may be influenced by two optimistic modeling assumptions of nuclear power plants with respect to flexibility and are hence seen critical. System cost in using nuclear power is higher compared to the CSP scenario, Chart A and Chart B. Other possible higher environmental impacts, waste, risk, or social impacts, acceptance, are not analyzed and would make a more comprehensive comparison difficult. From this situation arises that nuclear power plants may have advantages compared with CSP but probably cause higher system cost. The comparison of CCS and CSP in Chart C and D leads to the result that CCS induces less storage capacity in grid and transmission line expansion but brings about higher system cost, power plant capacity and curtailment. Both CCS technologies show a similar characteristic in the spider charts. The integration of CCS with the same capacity as CSP and nuclear leads to relative high curtailment. This result occurs because CCS has relative high variable operation and maintenance cost and is used as peak load power plant, thus energy from other power plants is more cost efficient than using CCS. The model integrates therefore more capacity of other, almost fluctuating, power plants, which leads to higher curtailment. Our results show the system cost deviation and full load hours of the examined technologies. The results in Chart A show that combined cycle gas turbine CCS has the lowest system cost deviation and nuclear power has the highest. This result seems reasonable due to an already past learning curve for combined cycle gas turbine and coal power plants with quite predictable cost. Furthermore, high cost uncertainty for nuclear plants is retraceable because nuclear projects have a high cost deviation often caused by construction delay and safety standards. Nuclear plants have thus the highest possible system cost expenditures but also high possible system cost saving. The system cost deviation for CSP is understandable since CSP technology still has to pass a learning curve and leaves us with a noticeable cost uncertainty for the time being. Comparing the quality of each technology, considering capacity but also annual energy, the annual full load hours in Chart B reveal that CSP and nuclear power plant are appropriate for base load configuration with recognizable higher annual full load hours than CCS technologies covering only peaks due to their higher operation and maintenance cost. The results show that CSP and nuclear have comparable operational behavior in the model, but CSP has a lower system cost uncertainty than nuclear power plants.
The evaluation of CSP, including a transfer of dispatchable solar power, nuclear and CCS power plants, shows that CSP is cost competitive and has an operational characteristic that leads to low curtailment and low system cost uncertainty in the energy system. Nuclear and CCS may have some advantages, especially in the reduction of grid and transmission capacity. CCS technologies are not competitive to CSP and nuclear plants due to their low average utilization that predominantly serves another demand segment. Thus, only CSP and nuclear power appear to be competitive within the analyzed criteria. Future analyses should include an approach regarding other sustainability indicators beside the used evaluation criteria. It can be concluded that the probability of CSP HVDC implies a possible integration of this technology according to its cost assumptions, thus dispatchable solar power, its transmission from desert regions has a high technological integration probability for the energy system as one major supplemental component. However, it should be noted that the cost assumptions of CSP and the pathway of HVDC are assumed as relative conservative and that CSP still renders a cost reduction till 2050 due to its advancing learning curve. Therefore, CSP HVDC has a high potential to be integrated. Nuclear plants and CCS are also possibly integrated, yet with a lower probability of nuclear plants than CSP HVDC or under the very optimistic modeling conditions for CCS. A wisdom from Christian Huygens says, "I believe that we do not know anything for certain, but everything probably." Feel free to follow and contact us via social media or email.